This is my presentation on my project one. I chose the energy efficiency dataset from the UCI Open Database. What this dataset is a simulation of different model or building shapes, and it gives you all of these different variables such as relative compactness, surface area, wall area, etc., and gives you two response variables, heating load and cooling load, to give civil engineers or whoever's working on this an idea of what these requirements are based on the building shape. What my project aimed to do was, can I build a model to classify heating load based on these different numerical variables? My analysis focused on these things. First, I looked at numerical statistics for my EDA. I looked at histograms to look at the different distributions. I did build a linear model, linear regression. So I needed my variables standardized. I looked at the correlation map to see if there was collinearity between any of my variables. And I also looked at pairwise relationships to see if I could pick up on any nonlinear relationships, strong linear relationships, which I can include in my model. I built three different models: linear regression, decision tree, and random forest. With each of these models, I used a tenfold cross-validation to build them to make sure that they weren't imbalanced based on specific portions of my data set. And then finally, I analyzed summary statistics for these models, and I chose the best model. So here is the first part of my EDA. It is my numerical statistics. Um, it didn't really uh, tell me a whole lot just looking at it. I relied more on the visualizations for my EDA, but you can see a couple of things. Uh, there is like significant variance in the scale of these different numerical variables. Like you can see surface area, wall area, how different they are from relative compactness. This was an issue because I tried to standardize these numerical variables. Again, we run into this issue of distribution. When we look at all our different variables, uh, because we are building a linear model, I wanted to standardize these variables. You can see some of the variables are more skewed than the other ones, uh, but this was helpful to look at just to know what pre-processing steps I would need. This was an interesting one. This was my correlation matrix. I decided to do a circle plot, and I picked up on a couple of interactions which were just noted. I didn't really find a way to use this information meaningfully in my analysis, but you can see here surface area and relative compactness are clearly, they have like some strong negative correlation. Again, with relative compactness and roof area, you see strong negative correlation. With surface area and roof area, you see a strong positive correlation. So there were definitely some interactions between these variables, um, which kind of led to me deciding to build more models other than just linear regression. Here are pairwise relationships between all of my models. You can pick up on some things like here you see a strongly negative relationship between relative compactness and surface area. And then you can pick up on a couple of other ones like that. Mostly I looked right over here for the heat load and cool load because these are the response variables. I couldn't see any sort of strong polynomial, quadratic, linear relationship with these. Maybe if I transform these variables, maybe I could see something more, but that's why I decided to build a tree-based model to try to capture relationships other than just the linear and polynomial ones. Also, because my data was so like this, like all my distributions were not the same, I wanted to build the tree-based model to try to have something better than just the linear regression. So here you can see this is just where I build the models. Here's I used tenfold cross-validation to build them. There wasn't really like a reason I chose tenfold over fivefold. I just did 10 folds just to do it. Here's my linear regression model. Here is my decision tree model, and here's my random forest model. And what I did was I tried to get these statistics, RMSE, R squared, and mean average error to compare my models at the end. Here are the steps I used to build these models, if that helps. But yeah, I first use this function to or this part to split my data set into 10 parts, and then I did it trained it using the crossfold validation. And then at the very end, I got these statistics from them, each of the models, and I output this here, but I also have a separate table for all of these statistics as well. Next was the visualizations. I had 3 models: linear regression, decision tree, and random forest, and I wanted to make a visualization for each of them. First, I wanted to try to put them all in the same plot. Even with the legend, I can't really tell what's going on in this plot. This is actually a scatter plot of the predictions of each of these models. If you look at my code, you can see better what I did, but yeah, I mean, you can see there's some model here, and these are the different classifications. It wasn't really clear. I ended up not using this model, but or this plot, but I included it in my analysis because it was something I did. Here is my linear regression predictions. Uh, Looks pretty good. There's not really too much I can say visually, but I used the a scatter plot of the actual data in these next 3 plots. Here's the decision tree predictions. It looks like this one is it's almost like zoomed in. Uh, doesn't look too good compared to the other ones. Here is my random forest predictions, my last model. Um, I had hoped that my visual representations would help me more on deciding which one was the best model, but I couldn't really tell, honestly. I included these visualizations because I thought it would look good as part of my presentation, but honestly, I just used the summary statistics to decide on the best model. So here is my final page where I decide the best model. Uh, and here are my 3 statistics. So I have RMSE, R squared, and MAE. So from this, we can see that the lowest RMSE is the random forest model, and the highest R squared is the random forest model, and the lowest MAE is the random forest model. So with that being said, I decided that the random forest model was the best for this task. It shows that it can predict, random forest can predict heating load with the highest accuracy, but is also the most consistent and reliable. Um, a couple of reasons why I think this is that it is a tree boosted model. So in case there were any nonlinear relationships present, it was able to capture those quite well. Also, because the variables were not of the same distribution, it might have performed better than the linear regression, even though I tried to standardize the data. I'd also like to say that the random forest obviously performed better than the decision tree because it's like an ensemble model. It involves all these different decision trees. So obviously, random forest is the best one. So uh, for a discussion for this, I like this project because it involved me comparing different models, like linear regression. That's like one of the first things I learned, but random forest and decision tree, you kind of always hear about them in the data science space, and I wanted to compare them on a real world data set. In the future, if I had to do this project again, I would probably use a larger data set. This one only had 768 rows, which was convenient, but yeah, I would like to build more robust models. But overall, this was a great experience. Conclusively, random forest is the best model on this data set at classifying heat load for these different residential buildings.